So a very good morning everyone. Welcome to the foundation course by IMS GATE Academy. Myself Prateek Mishra and we are discussing about the fundamentals of strength of material. In the previous sessions, we have covered almost all the fundamentals that are required to solve the application-based question of strength of material that are asked in GATE and other technical examination. Today we will going to continue with the bending stresses and we will going to see what do we mean by a pure bending equation and how do we basically apply this pure bending equation. So let's start with the pure bending equation or the equation of pure bending. So please give the heading equation of pure bending. In the previous session, I have already told you that pure bending means where the value of shear force is zero and only bending moment exists. So that span of the beam where the value of shear force is zero and only bending moment will exist, that span of the beam will be under the action of pure bending. Okay. Now, if the beam is under the action of pure bending, then how the bending stresses are developed, what are the variation of bending stresses and how to calculate the bending stresses, that is what we want to going to discuss today, right? In the previous session, we have already taken care how to calculate the depth of neutral axis. Neutral axis is that fiber which neither elongates nor contracts, or I can summarize neutral axis as that fiber over which no deformation happens. And also the value of stress at the neutral axis is also be zero. Okay. Let me consider one body which is under the state of pure bending. This is my body. And this body is under the state of pure bending and this is the neutral axis. When only bending moment is there, when only bending moment is acting over the span like this, when only bending moment is acting over the span like this, then this body is said to be under the state of pure bending. Okay. Okay, so this is the neutral axis. I'll name this neutral axis, this point as, I'll name this as A. And I'll name this as point B. This is my point AB. Okay. I want to calculate the distribution of stresses in the cross section. Means if we move anywhere above or below from the neutral axis, how the variation of stress will happen and how to calculate the value of bending stress at a particular depth y. Okay. So for that, I'll choose one fiber like this. This is my fiber that I have chosen. Over this fiber, I want to calculate the value of bending stresses. And this fiber is at some depth y from the neutral axis. Let me also name it. This is D and this is E. Okay. So initially, whatever is the length of AB, same is the length of DE. So AB is equal to DE. AB is equal to DE initially. When this beam will going to bend or when this span will going to bend, it will going to take a shape like this. This is the shape of beam which is bended. This is the shape of bent beam. Okay. Now observe this very carefully. This is my neutral axis. This is NA. And this is my neutral axis. When you just extend these two members, or when you just extend these two, right, you will find that this bent beam is forming an arc whose center is at this point O. Okay. And the radius of this beam, and radius is always measured from the neutral axis. This radius is R, right? And this radius is from the center till the neutral axis. Okay. And the angle made by this bend is theta. Observe this very carefully, right? This is the neutral axis and this is how beam is bent. And this bent beam has a radius R and the angle subtended by this bent beam is theta at the center. Okay. So if I want to ask you what is the length of this arc AB? What is the length of this arc AB? So length of this arc AB is R into theta. You can clearly say that the length of arc AB is R into theta. This is R into theta is the length of this arc AB. Okay. My DE, this DE fiber will extend to DE dash. This is D dash and E dash. This is D dash and this is E dash. Okay. What is the length of D dash and E dash? If this distance is Y, this distance is Y. What is the length of D dash and E dash? The length of D dash and E dash, you will say that, sir, it is R plus Y. That is the total length from this point D dash till O. It is R plus Y into theta. The increased length of D dash and E dash is D dash and E dash is R plus Y into theta, right? Okay. Two diagrams are in front of you and it is clearly visible that initially the length of DE is equal to the length of AB, right? Even after deformation, the length of AB will not change because AB is nothing but the neutral axis which neither undergoes any kind of deformation, neither contraction nor elongation, okay? And from here only, I have calculated D dash E dash, which is R plus Y into theta. This is R plus Y into theta, right? Observe this. So I'll write strain in DE, strain in fiber DE, that is epsilon DE. Strain in fiber DE is equal to change in length of DE, that is D dash E dash minus DE divided by DE, original length. So strain in DE is equal to D dash E dash minus DE upon DE. This is the strain in DE. Okay. Now this DE is equal to AB. So I will write D dash E dash minus AB divided by AB. Because I know the value of AB, that's why I am writing DE is equals to AB. Now just substitute the value. So you have epsilon DE is equal to D dash E dash is R plus Y into theta minus AB, which is R theta, divided by R theta. So you will take theta common and theta will going to cancel out. R plus Y minus R divided by R. Okay, so this is epsilon DE is equal to R plus Y minus R divided by R. So this R and R cancels out and you have epsilon DE is equals to Y by R. Now this epsilon dE can be written as sigma by E is equals to Y by R. So from here you get first relation, that is sigma by Y is equals to E by R. Sigma by Y is equals to E by R, right? You can just note this down. So this is the first relation of bending equation. This is my relation number 1, right? Now coming back to the second relation. When you take this kind of beam, when you have a beam like this, right? When you have a beam like this, I am considering the same beam with neutral axis. This is my neutral axis. For this neutral axis, this is DE. So this is AB, this is A, this is B, and this is DE. Right? Now over this beam, the total moment is M. The total moment is M. The total moment is M. In order to calculate this moment, how much is the amount of moment that is acting over this DE? So what you have to do is just consider this area. Just consider this area, and this area is dA at a distance of y. This is at a depth of y, and this area is dA. Just calculate the moment due to this area. Stress value, you know, stress is equals to sigma into dA. Stress is sigma. Force due to that stress is sigma into dA, and moment due to that force is equal to y into sigma into dA. What I am trying to say is, if I want to calculate a force over this area of length dy, so force dF is equals to sigma into dA, right? Okay. Due to this force dF, the moment present in this strip dA is equal to dm, which is equal to y into dF. And this y can be, dF can be written as y into sigma into dA, right? So this dm is equal to sigma into y into dA. Just check this and get the value of moment. Just substitute the value of this sigma. So this is equal to dm. This we have just now calculated sigma. It is E into y by r. So this is E into y by r into y into dA. So your dm is equal to E by r into y square dA. In order to calculate the complete moment, we have to integrate this. You have to integrate this expression. E by r is a constant, that's why they are out of integration. And when you take this y squared dA, this y squared dA is nothing but the second moment of area, and second moment of area is nothing but moment of inertia. Second moment of area is moment of inertia. Second moment of area is moment of inertia. So you can clearly write that m is equals to E by R into I, where I is the moment of inertia. So from here you have m by I is equals to E by R. And we know that this E by R is also equal to sigma upon y. This is also equal to sigma upon y. So this gives you the complete pure bending equation. This gives you the value of bending stress at different fibers from the neutral axis. What this y tells us is, observe this. If you have a beam like this, I am taking a wider section. This is my neutral axis. This is my neutral axis, right? So if I move any distance y from the neutral axis, this is my neutral axis. If I move any distance y from the neutral axis, I will get the value of bending stress at this fiber. The value of bending stress at this fiber, right? This is my value of bending stress at this fiber. Similarly, if I move anywhere down from the neutral axis, I will get the value of bending stress at this fiber of the beam. Okay. So basically, this is the cross section of the beam. If anywhere from the neutral axis I'll move, through using this equation, I'll get the value of bending stress at this fiber. Now, observe this. If I need to plot the bending stress distribution, so this we have already seen. Once again, I am drawing this bending stress distribution. For suppose this is my cross section of the beam, okay. For this cross section, this will be my neutral axis. This is my neutral axis like this. For this neutral axis, I'll just draw the top fibers and bottom fibers also. So this is my top fiber of the beam, and this will be my bottom fiber. So if I need to plot the bending stress distribution, first thing I will plot is the bending strain distribution. So this is the bending strain. This variation is the value of bending strain. So this is my bending strain, right? This is my bending strain. I have observed that means whatever bending moment I have applied, due to which the upper fibers are in compression and bottom fibers are in tension. So upper fibers will going to get contracted and the lower fibers will going to expand. And due to the assumptions that we made in the while discussing about bending. Hello, a very good evening. Siddharth Pandey is saying hello, okay. So due to the assumptions made while we discussing about the assumptions in pure bending, one assumption is plane section remains plane even after bending. So from that assumption, we came to know that the variation of strain is linear from the top fiber to the bottom fiber. If the top fibers are in compression, they will going to contract, and bottom fibers are in tension, they will going to expand, right? So this is my strain distribution. So this is epsilon C max. And the maximum value of strain will happen at the extreme fibers. And this is epsilon T max. Right? So this is the value of strain and how it is varying. Similarly, if I multiply this strain with the Young's modulus, that is how you can relate. Or second thing, using this bending equation also, you can relate that this bending stress is directly proportional to strain. So when you write bending stress, sigma is equal to m upon I into y. Like that, you can understand that sigma is the bending stress which will be linearly varying with the value of y. So at the position where the value of y is 0, the value of sigma will also be 0. The value where the y is maximum, at that point the value of sigma will be maximum. So from here also you can understand that at the neutral axis the value of bending stress is 0, and at the extreme fibers the value of bending stress will be maximum. So when you observe this and draw the bending stress distribution, your bending stress distribution will be like this. This is your bending stress distribution, right? Wherever the compressive stresses or the compression will act, there you will find the value of compressive stresses. So this is your sigma C, and this sigma C is maximum at this fiber, that is the extreme fiber. And at the bottom extreme fiber, you have sigma T maximum. You have sigma T maximum. So at the extreme fibers, the value of bending stresses will be maximum. Now, how to calculate this value of bending stress? For that, we need to use the bending equation. And from bending equation, we know that the value of bending stress will vary linearly with the value of y. So if you move anywhere from the neutral axis, for suppose, if you move the y distance from the neutral axis, if this is my y distance from the neutral axis, the value of bending stress at this point will be this. This is the value of bending stress at y distance from the neutral axis. So simply, if a question is asked in the exam that calculate the value of bending stress at some distance y from the neutral axis, so what you have to do is you have to simply consider the bending equation, that is m upon I is equals to E upon R is equals to sigma upon y. With respect to the data given in the question, you can use any of the combination. Either you can use m upon I is equals to sigma upon y, or you can use E upon R is equals to sigma upon y, right? So any of the combination you can use to calculate the value of sigma, which is the value of bending stress at any distance y from the neutral axis. Okay, one more thing. Here we have discussed that the beam will going to bend like this, right? So this R is the radius of bend, means from the center point till the neutral axis, this is R, which is the radius of bend. Now the curvature of bend can simply be said as 1 by R. So if in the examination a question is there to calculate the curvature of the bend, so curvature is simply 1 by R. curvature is 1 by r. That's all. So this curvature is simply 1 by r. So if you need to calculate the value of curvature, you have to just observe 1 by r, and that will directly give you the value of curvature, right? Okay, so let's do some problem. So here I have we'll take some big problems, right? We'll take some big problems. One I section is given to us like this. One I section is given to us. This is the symmetrical I section. Both the dimensions are equal. So this dimension is 100 mm. This is 100 mm. This is 20 mm. This is again 100 mm. This is 20 mm. This is again 100 mm. And this is 20 mm, right? So due to this symmetry in this I section, one thing is sure that neutral axis will pass from the center, right? So neutral axis will pass from the center of this rectangle because either of them are symmetrically placed. Okay, so this is given to us. We need to calculate. So one more data is given to us, the value of moment. The value of moment is acting 650 kilonewton meter. This is the value of bending moment which is acting over this beam, right? Young's modulus is 2 into 10 raised to power 5 megapascal. Now you need to calculate the value of maximum bending stresses. Calculate maximum bending stresses that will come over this beam, right? So you have a beam cross section. The dimensions of the beam cross section is given to us. The value of bending moment coming over the beam is given to us. This is the sagging bending moment. That is, the upper fibers are in compression and bottom fibers are in tension. The value of Young's modulus is also given to us. We need to calculate the maximum bending stress, right? Now, one thing is sure, that whenever we will be analyzing any beam, okay, the value of maximum bending stress will be at the extreme fibers, right? If I talk about the neutral axis will pass through the center of this rectangle, and about this neutral axis, the section will be symmetrical. The section will be symmetrical, okay? Just try this question. Just try this question. Take the screenshot and try this question. Okay, so welcome back. I hope you have tried this question. You need to calculate the value of maximum bending stress for this cross section of the beam over which a bending moment of 650 kilonewton meter is acting, right? So if I need to calculate the maximum value of bending stress, I know that I need to calculate the value of stresses at the extreme fibers, right? In this extreme fibers, the value of bending stresses will be maximum. So for calculating Y sigma max, I need to focus on Y max. Wherever the value of Y will be maximum, at that point, the value of sigma will be maximum, right? So I'll use this relation M upon I. So M upon I is equals to sigma upon Y, which is also equal to sigma max upon Y max. So Y max I know. If I take the neutral axis, from this neutral axis, this extreme fiber is at a distance of 20 plus 50. Half of 100 is 50. So this is 50 plus 20, 70. Same if I go at the bottom side of the neutral axis, I have 50 plus 20. So again this is 70. So this section is symmetrical about the neutral axis and the value of Y max is 70. So one thing I know that Y max is 70. Y max is 70 mm, right? Now second thing, moment of inertia, this moment I know, it is given as 650 kilonewton meter. So M upon I, M I know, Y I know, or Y max I know. I need to calculate moment of inertia I, right? So for calculating moment of inertia I, so next step is calculation of moment of inertia I. So let me draw this section quickly. So this is my cross section. This is 100 mm. This is 20 mm. This one is 20 mm. Okay, so first of all, and this is my neutral axis. I want moment of inertia about this neutral axis, right? I want moment of inertia about this neutral axis. So how to calculate moment of inertia for this cross section? First of all, I'll calculate moment of inertia for this rectangle corresponding to its CG. This is the CG of this rectangle, right? So the moment of inertia of this rectangle about its CG is, okay, so I'll write everything in parts. It is B, that is 100 into 20 cube divided by 12. This is 100 into 20 cube divided by 12. So this is the moment of inertia of this rectangle about its CG. Now I need to transfer this moment of inertia about neutral axis. So using the parallel axis theorem, what parallel axis theorem says that if I need to calculate the moment of inertia of this rectangle about this neutral axis, it is equal to the sum of moment of inertia about this CG plus moment of this area or second moment of this area about neutral axis. So this is my lever arm and this distance is y1, right? So moment of inertia about CG was 100 into 20 cube divided by 12 plus A into y1 square plus A, and A is 100 into 20, 100 into 20 multiplied by y1 square. So this y1 is, this is 50 and this will be 10. So y1 will be 50 plus 10, which is 60. So this is 60 square, right? Now this is the moment of inertia of this rectangle about this neutral axis. Similarly, if you calculate the moment of inertia of this neutral, of this rectangle, The dimension of this rectangle is also same. This is 100 mm. Width is 20 mm. Right. So moment of inertia of this rectangle about CG is 100 into 20 cube divided by 12. Same as this first term. Now look into the second term. The distance of the CG of this rectangle from the neutral axis. This distance is again, this is y2. And this y2 is like 50 plus 10, 60. So it is again equal to y1, right? So when you transfer this moment of inertia about neutral axis, so the first term is also same. Second term, area is 100 into 20 and this y2 is again 60. So this term is also same. So similarly, I'll multiply this with 2. So because this term will come twice, one for this upper rectangle and one for this lower rectangle. Now looking into this one rectangle, the center one, right? The web of the section. So this is 20 mm and the depth of the section is 100 mm. And the CG lies at the neutral axis. Okay. So I have to simply take the moment of inertia of this rectangle simply, right? So moment of inertia of this rectangle is 20 into 100 cube divided by 12. So this is 20 into 100 cube divided by 12. So from here I have calculated the moment of inertia. Okay, I know the bending moment. I know the moment of inertia. I know the value of y max. Y max is the distance of the extreme fiber from the neutral axis, which comes out to be 70, right? From here, I can get the value of sigma max. So calculation of sigma max. Calculation of sigma max. So sigma max is equals to m by I into y max. So sigma max is equals to m, which is 650 kilonewton meter. So this is 10 raised to power 6. 650. Now it will be Newton meter. I'll write this. This is Newton, mm. This will be Newton mm. Then I'll write y max. So y max is given as 70 mm. Okay. And why I'm converting this into Newton and mm? Because the moment of inertia we have calculated in mm. Now calculating the moment of inertia, this you can do the quick maths and get me the value of moment of inertia. Even I'll try. Just do the calculation quickly. So this will be like 100 into 20 cube divided by 12 plus 100 into 20 into 60 square into 2 plus 20 into 100 cube divided by 12. So it comes out to be 16.2 into 10 raised to power 6. So this is 16.2 into 10 raised to power 6 mm raised to power 4, right? So this 10 raised to power 6 and 10 raised to power 6 will going to cancel out, and you have 650 into 70. 650 into 70 divided by 16.2. So this comes out to be 2808. So this sigma max is 2808.64 megapascal. Newton per mm square or megapascal, one of the same thing, right? So for this question, this is the value of bending stress that will develop in the extreme fibers. No doubt it's a very huge value, but it's again a hypothetical question, right? Not a practical one. Okay. Now one more thing I would like to tell you. This M by I is equals to sigma by Y, right? This M upon I is equals to sigma upon Y. And right now we have seen that this M upon I is equal to sigma max upon Y max. This sigma max upon Y max. If you just rearrange this, you have M is equals to I by Y max into sigma max, right? So this I by Y max is termed as the parameter Z, and Z is known as the section modulus. Z is known as the section modulus, right? So section modulus Z is equal to I by Y max. And if I'm using Y max, right, this is very precise. I'll be using Y max every time to calculate the value of Z, which is the section modulus. So along with Y max, I will be using sigma max. So I will write M is equals to Z into sigma max. Z into sigma max. Now observe this. This section modulus Z is the characteristic property of a particular cross section, right? This Z will going to tell us what is the value of moment of resistance that a cross section can offer, okay? This Z is used to calculate the value of moment of resistance. There is a difference between applied moment and the moment of resistance. It doesn't matter, it's totally in your hand, whichever kind of bending moment or whatever the value of bending moment you want, you can apply over the section. But every section has its capacity to resist that bending moment, right? And we are talking about that capacity. The capacity of a cross section to resist bending moment is termed as moment of resistance, right? I'll explain you this. For suppose there is one cross section made up of some material, right? It is totally on your hand whatever the value of moment you can apply over this cross section, right? So the value of moment that you apply over the cross section is known as the bending moment or the applied moment. This M is known as applied moment. And this applied moment is due to the external source. This applied moment is due to the external source. So it's totally dependent on the external source, whatever the amount of bending moment they want to apply over the cross section, right? But this cross section has some internal capacity to resist this applied moment. That internal capacity of the cross section to resist this applied moment is termed as moment of resistance. So moment of resistance is MR. It is the internal capacity of the cross section. It is the internal capacity of the cross section. Internal capacity of the cross section to resist the bending moment. to resist the bending moment or the applied moment. I'll write here or applied moment. So this applied moment is totally dependent on the external source, but this moment of resistance is the internal capacity. It depends on the cross section, right? So many times you are asked to calculate the moment of resistance. Moment of resistance, first of all, has nothing to do with this applied moment, right? This applied moment is due to the external source, but moment of resistance will always be internal and depend on the maximum stress a material can bear. In our design, the maximum value of stress that we want to apply over the material is the value of yield stress. Okay, we do not want material to yield like or undergo plastic deformation. So the maximum amount of stress that we want to develop in the material is the yield stress. Okay, you can understand like this: the maximum amount of stress due to bending in a material is known as its bending strength, right? So this moment of resistance is totally internal. It is the internal capacity of the material or the cross section to resist the applied moment. The maximum applied moment a material can resist or a cross section can resist is known as the moment of resistance. So moment of resistance MR is equal to section modulus into the bending strength. That is the maximum amount of stress that we want to develop in the cross section due to the external load. Observe this very carefully. Moment of resistance is equal to the section modulus into sigma max, and sigma max is the maximum amount of bending stress that are developed in the cross section. Okay. From here, you can very clearly identify that the moment of resistance of the material can be improved by improving two things. First one is, if you improve the quality of the material, the value of sigma max will improve. And if the sigma max will improve, the moment of resistance of the material can improve. Okay, you can just consider an example of wood, aluminium and steel. Wood, aluminium and steel, right? As you improve the quality of the material, the value of sigma max will increase. The value of sigma max will increase. The value of sigma max will increase. That is the maximum stress that a material can bear, that can increase, right? At a very low value of stress, wood will fail. At somewhat intermediate value of stress, aluminium will fail. But we know that steel has a very good yielding stress value. And the yielding stress value for steel is more than aluminium, and for aluminium, it is more than wood. So fracture stress for wood is less than the yielding stress for aluminium, and the yielding stress for aluminium is less than the yielding stress for steel. This we know. And this yield stress we are talking about as the maximum stress a material can bear, right? So if you improve the quality of the material, without even changing the cross section, using the same dimension, your value of moment of resistance will improve. So moment of resistance for wood, just by improving the material, you have improved the moment of resistance for a particular cross section. So moment of resistance offered by a cross section of wood will be less than moment of resistance offered by aluminium, and this will be less than moment of resistance offered by steel. So I think this is simple. So for a particular cross section, if you need to improve the moment of resistance, you have to improve the quality of the material. And I think using your common sense, this is a very, very basic concept that if you improve the quality of the material, its internal capacity will going to improve, and you can apply more amount of load, and that material can bear more amount of load that is applied over it, right? Okay. So this is the first way for improving the moment of resistance. So moment of resistance can be improved by improving the material. So I am writing this as a note point. Moment of resistance for a particular cross section can be increased by increasing the quality of the material, or by improving the quality of the material. By improving the quality of material, right? So this is the first way of improving the moment of resistance for a particular material. Okay. Now observe this equation once again. Moment of resistance is equals to Z into sigma max, right? Now if we are talking about the same material, for same material means the value of sigma max is constant. For same material means sigma max is constant. For this same material, how we can improve the value of moment of resistance? So for the same material, if you improve the section modulus, right, then you can increase the moment of resistance. So for the same material, if the value of Z can be increased, then in that case, moment of resistance will going to increase. In order to increase Z, just look into the parameter Z. Z is equals to I by Y max. I by Y max, okay. So if you increase the value of Z, you can increase the moment of resistance. Z can be increased by increasing the moment of inertia about neutral axis. Okay, how can Z be increased? Z can be increased by increasing the moment of inertia about neutral axis. Okay, if this is my neutral axis, right, and this is my cross section, and this is my cross section, right? For this cross section, and this is my neutral axis, if I want to increase the value of section modulus Z, I have to increase the moment of inertia. And if I have to increase the moment of inertia, what I want is, whatever is the content of the material which is present in the cross section, it should be distributed away from the neutral axis. Means, if you just take this material and you shape it like this, right? If you shape it like this, if you take the material and you shape the material like this, now, and when you compare the moment of inertia for the rectangle which was there earlier, and now this I section where more amount of mass is distributed away from the neutral axis, you will find that the moment of inertia for this I section will be more than this square section. So moment of inertia for I section is more than moment of inertia for the rectangular section, right? So whenever more amount of mass is distributed away from the neutral axis, away from the neutral axis. If more amount of mass is distributed away from the neutral axis, the value of moment of inertia will be more. And if the value of moment of inertia will be more, your moment of resistance, if value of moment of inertia will be more, your section modulus will be more. And if your section modulus is more, then the value of moment of resistance will be more, right? So that's why when you see maximum number of beams, right? When you see all these beams, for laying of these beams, the preferred section is the I section. For beams, the preferred section is the I section, because for I section, the majority of mass is distributed away from the neutral axis. And when you talk about this mass which is present away from the neutral axis, these mass will going to take the majority of the bending stresses. This mass will going to take the majority of the bending stresses. When you observe this, you will find that this mass and this mass, which are away from the neutral axis, these mass will take majority of bending stresses. Majority of bending stresses, sigma B, right? So if mass is distributed away from the neutral axis, it will take more bending stresses. And if the material is taking more bending stresses, it has a strong moment of resistance. So moment of resistance is basically dependent on two properties. First one is, if you improve the quality of the material, the value of yield stress will increase. And if the value of yield stress will increase, it means that the strength of the material in bending is improving. And if the strength of the material in bending is improving, it means the material can bear more amount of load with same cross section. Second, if you do not want to change the material and you want to increase the moment of resistance, so what you can do, you distribute more mass away from the neutral axis and less mass at the neutral axis. Because in the vicinity of the neutral axis, it is very much clear that the value of bending stresses are very negligible. And the value of bending stresses are huge when we move away from the neutral axis. Okay. So this is how the variation of bending stress will happen. And using this moment of resistance, you can clearly identify how much amount of bending moment can be beared by the particular section. So I hope you have found this session very useful and you have learned a lot of new concepts and a lot of basics regarding the bending stresses. So I, Prateek Mishra, signing off. I hope you might have enjoyed this session. Please like, share and subscribe the channel and share with your friends to share the knowledge. Thank you so much for listening patiently. Have a great day ahead. Thank you so much.